In this video, we are going to discuss what happens to pyruvate following glycolysis. Cellular respiration is defined as the complete oxidation of a glucose molecule to yield energy in the form of ATP. Recall from the Carbohydrate Catabolism Part 2 video that oxidation is seen as hydrogen ions are stripped from the glucose molecule, resulting in the formation of reduced electron carriers. The reduced electron carriers that were produced in glycolysis included two molecules of NADH, as hydrogen atoms were removed from glyceraldehyde 3-phosphate. So at the end of glycolysis, only 2 of the 12 hydrogens have been removed and transferred to electron carriers. There are hydrogen atoms remaining on the 2 pyruvate sugar molecules. In the next steps of cellular respiration, the goal will be to finish removing the remaining hydrogen ions in order to complete the oxidation of the molecules. Cellular respiration is said to occur in phases. Some textbooks and videos describe the process in 3 phases: glycolysis, the citric acid cycle, and the electron transport chain. Before we proceed to the next step of cellular respiration, let's look at a couple of images. The image on the left of the screen is showing the last of the steps of glycolysis. The image on the right shows the citric acid cycle. The starting compound for the citric acid cycle, acetyl-CoA, is shown in better detail in the enlarged image at the bottom on the right of the screen. Looking at the 2 images on the screen, I want you to count how many carbon atoms are present in a single molecule of pyruvate and a single molecule of acetyl-CoA. Do not misinterpret the CoA as being a carbon molecule. It is crossed out in the image to assist you. Now that you've had time to look at the number of carbons in pyruvic acid and acetyl-CoA, let's talk about why pyruvic acid will not directly enter into the citric acid cycle. As you learned, pyruvate has 3 carbon atoms. The starting molecule acetyl-CoA has only 2 carbon atoms. Acetyl-CoA will combine with the last molecule of the citric acid cycle, oxaloacetic acid, to produce the first product, citric acid. The cycle is named after this first product. Look closely at the number of carbon atoms in oxaloacetic acid and citric acid. You should see 4 carbon atoms in the oxaloacetic acid and 6 carbon atoms in the citric acid. So in order to run this cycle, the molecule that will enter from glycolysis must be only 2 carbons. So there has to be an extra step in the cellular respiration process between glycolysis and the citric acid cycle that will convert the 3-carbon pyruvate to the 2-carbon acetyl-CoA needed as a substrate in the citric acid cycle. This extra step is known as the intermediate or preparatory step. In the intermediate step, pyruvate undergoes a decarboxylation, meaning that a carbon dioxide is removed from the molecule. Carbon dioxide is a waste product. The remaining molecule is acetate. The acetate molecule then undergoes a redox reaction in which hydrogen is removed from acetate and passed to the electron carrier NAD, and coenzyme A is bound to the acetate, resulting in the production of the reduced electron carrier NADH and a molecule of acetyl-CoA. It is the acetyl-CoA that will then enter the citric acid cycle. Remember, 2 molecules of pyruvate were produced in glycolysis. Therefore, for each glucose molecule, the preparatory step must occur twice.